Hi again, I'm Dr. Matthew Michael. I'm going to be continuing on my differing reviews of differential equations. Today I'm going to do some off of a PowerPoint that I've done, as well as one off of a couple of things that a friend of mine wrote on for his PowerPoints. So we're going to be dealing with what happens when we can't do a series solution around an ordinary point. So here we go. So let's focus on what I did first, and we'll continue on with his. So remember, number one, that an ordinary point is that when you plug it into this differential equation, it's when that big P of x does not equal to 0. Any other point, when I plug in any point where I plug in to big P of x and it equals to 0, we call that point a singular point. And as we've talked about before, the cases that you'll be most likely seeing in my class or in an intro to differential equations class will be where P, Q, and R are polynomials, maybe trig, or some simplistic thing that you can find in Maclaurin or Taylor series, in which case we call them analytic, more for the most part. Then we're going to be dealing with that. So, singular points. Let's look at the Bessel equation, a famous equation that we play a lot with. It even has a specific solution, Bessel solutions. If we take a look at the Bessel equation and we look at the very, very front, we see that a big P of x is equal to x squared. Solve x squared for 0, and surprise, surprise, x is equal to 0 is a singular solution. Every other point, any non-zero value for x is, surprise, surprise, ordinary. So in this case, I cannot allow my previous slideshow talking about how to make ordinary solutions, blah, 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 blah. That will not work in this case. It just will not work. So let's continue on with the Legendre equation. This case, I have P of x is equal to 1 minus x squared. Set that equal to 0, I get x is equal to, surprise, surprise, x is equal to plus and minus 1 is, or r, are singular points. In this case, x is equal to 0 is an ordinary point. They'd have a radius of convergence of 1, since there's a distance either direction of 1. So, but I could also choose ordinary points outside of 1, say 2, 522. All those are ordinary points. So, if we attempt to just use those points that we talked about last time around our singular points, or a neighborhood around those singular points, those points will severely fail. Once again, that term analytic pops back up. We don't have Taylor series expansion around those points. Oftentimes we have what's known as poles or other problems that occur, whereas Taylor series, you'll see we're in x to the n is some positive integer. Oftentimes near your singular points, at best you're going to get negative numbers, like -1, -2, maybe higher or more negative. And so what we're going to need to do is be more careful about our general series expansion, and we're going to talk about that next video more in depth. And so, but the thing is around these singular points, the solution behavior is very important. Those singular points drag all other their surroundings in their neighborhood into some crazy values. And so it becomes unbounded. Magnitude will jump all sorts around, and oftentimes these occur near sharp points or corners in solution. For example, a singular point might be if you're considering a wave, you're modeling a wave for surfing. That singular point is when that wave is just crashing, right? When you see the beginning of the white that singular point in time happens right when the crest begins to cover and the white foam occurs. So those are when our singularities really kick in, because we've really been dealing with continuous functions because they're nice, they're pretty, we like them. And in fact, our numerical solutions, we talked about Euler method definitely doesn't work, and all sorts of craziness can happen near these points. So we need something else. And so for this time, next time we'll be talking about this behavior, that we might be able to plug in another solution type, might be able to fix our series. But this time, we're hoping against hope, that we might be able to get a specific type. And in fact, we can. We call these the Euler equations. And these will act just like we did with constant coefficients. And we can actually form a characteristic equation. If, I say if, when we take a look at our singularity and compare it to the rest of the terms of our series, our differential equation, do you see that when I have my second derivative here, I have a second order term involving the singularity. When I see a first order, it has the same term but first order. And with zero order, original function, I have zero terms in front of it. We call this an Euler type equation. See. Now, for this case of simplicity, I'm going to be dealing with x not equal to 0, but this works for all cases. It gets really messy if you don't make x not equal to 0, but the method still definitely works. So, when x not is equal to 0, what does this mean? Well, we plug that in, we get x squared y double prime plus alpha xy prime plus if beta y is equal to 0. Plug in our assumed solution. Let's just assume that y is equal to x to the r, just like we assumed for constant coefficients that it was e to the rx, or e to the rt. When we plug that in and we take the appropriate terms to plug in, we notice an x to the r term keep popping up, just like we did when we originally started solving for second order systems with constant coefficients. Factor out that x to the r, and we get our characteristic equation inside our brackets. Now, we already said that we don't like the singularity, and our x to the r term came from our singularity point. So, we're going to assume we're not at the singularity. Not there. At any other point, if this method works, it'll work. It won't. What happens is the solution doesn't cause a singularity except for at that single individual point. Think of it like a hole in Calc 1, where it didn't affect anything else except for at that precise moment in time. It was like dividing x squared minus 4 by x minus 2. That just becomes x plus 2, except for at the point when x minus 2 is equal to 0, or x is equal to 2. And so we have that little hole that we plot, inside of our x plus 2 line. The same thing happens here. So assume that x does not equal to 0, or x is not equal to our singularity point, because that would be bad news. Then we have our characteristic equation. So solve that characteristic equation for r, and you can see those values of r that it'll work to kind of smooth over our singularities, to make a whole rather than an infinite discontinuity. So take a look at this equation. X squared y double prime minus 2y is equal to 0. This case clearly has a singular point of x not is equal to 0. Notice that the y prime term has a 0 coefficient in front of it, so my alpha term is going to be 0. My beta term is going to be negative 2. Plug that into your equation. Your characteristic equation becomes r times r minus 1 plus 0r minus 2, or r squared minus r minus 2 is equal to 0. Be careful that this isn't r squared. This is r minus 1. because I'm using a polynomial, not an exponential. I can easily factor this, and I get two R values, just like I did with constant coefficients before. So I have solutions, c1 x squared plus c2 x to the negative 1. And notice that while x squared is analytic, or I can find a series or its continuous function, x to the negative 1, or 1 over x, does not have a Taylor expansion. It's messy. Or at least it's messy near around the point x not equal to 0. Here's another one. Simple case. Still x not equal to 0. X squared y double prime minus 2xy prime plus 2y is equal to 0. So in this case, the thing in front of xy prime is negative 2. The thing in front of y is 2. So alpha is equal to negative 2. Beta is equal to 2. Plug it in. Expand. You can easily factor this. X minus 2, x minus 1, or r is equal to 1 and 2. So I have this pretty case. So it might be that I can find a series solution around these points if I'm careful about it, but I have to be, like I said, very, very, very careful. And so this works in a general context if I have this basic form. So these Euler type solutions give us a way to classify our method, or methods that we've been doing, because next time it's going to be very careful. We're going to be able to make our equations look like Euler equations sometimes. In those cases, we can start getting ideas of what to do. But this Euler type equation allows us to classify our different types of singularities. Are they well behaved? Are they not so well behaved? So we divide by p of x. We know the singularity occurs at those x naught values because p of x naught is equal to 0. But if it's not too bad, if it doesn't go to infinity too quickly, i.e. limits, we might be able to salvage some using what's known as the method of Frobenius. I'm not going to talk about it a lot in this class, but if I multiply my q over p by a linear x minus x naught term, and I take the limit, and it is a finite number. And if I do the same thing with r over p, but with a quadratic, I get a finite number. This is good enough to call it a regular singular point. It is regularized. That at these points I'm going to be able to do something very similar to what I did in this section. If it doesn't, if when I multiply this out, it doesn't smooth out, it doesn't regularize, I call it, surprise, surprise, an irregular singular point. So let's look at a couple of these. So let's look at the Bessel equation. Singular point at x naught is equal to 0. So this is only singular point. So let's see if it's regular or not. Well, q of x is going to be x. P of x is going to be x squared. So plug it in. Limit as x goes to x naught of x minus x naught times q over p, or the limit as x goes to 0 of x times x over x squared. So that's the limit as x goes to 0 of x squared over x squared, or the limit of 1. So that's equal to 1. 1's a finite number. I like 1. Let's do the other one. So r of x is that x is the term in front of my function y here. So that's going to be x squared minus mu squared over x squared. Plug that in. The x squareds cancel out. I'm left with x squared minus nu squared. Well, as x goes to 0, x squared also goes to 0, so I'm just left with negative nu squared. So for all Bessel equations of order nu, at least, well, in this form at least, where x naught is equal to 0 is a singular point, it is a regular singular point. Let's take a look at this equation. 2x, x minus 2 squared, y double prime, plus 3x, y prime, plus x minus 2 y is equal to 0. Think for a second. What are your two, hint, there's two singular points? Well, P of x, that thing in front, is equal to 0 when this all equals to 0. So 2x is equal to 0 when x is equal to 0. And then I have x minus 2 quantity squared equal to 0. Well, the only case that happens is at 2. So 0 and 2. Let's check 0. Well, 0 is a regular point because when I plug everything in, things cancel out. Notice the x and the x cancel out. And I'm left with 3x over 2x minus 2 squared. So the top becomes 0. The bottom becomes 2 times 4, 8. So 0 over 8 is 0. Do the same thing again. X cancels out with the x on the bottom. So I'm left with an x on top. And x minus 2 cancels out. Here, cancel. So I'm left with the limit of x over 2 times x minus 2. When x goes to 0, the top goes to 0, the bottom goes to negative 4. 0 over negative 4 is still 0. So because both limits are finite numbers, I don't care that they're 0, it's a regular singular point. Let's check our other value, 2. Unfortunately, it doesn't work. Plug in my x minus 2 in front, and 3, my q of x over p of x. Unfortunately, because there's that square term there, and there's no x minus 2 term here, it doesn't cancel out like it should if it was a regular point. So because this limit does not exist, we call it an irregular singular point. So, I mentioned before some differential equations here. Let's get some more practice here. So we talked about how to do this, but what about those other special cases? So, when I'm dealing with these right here, so this is another way of looking at the Euler equation. X squared y double prime plus alpha x y prime plus beta y. And I talked about this characteristic equation before. We can solve this by moving our form from below right here to this form here. So notice the alpha and negative 1. This is just a quadratic, so this is the general form for your r's using the quadratic formula. I like to factor. Most of the cases you're going to be doing, you can factor, but the quadratic formula will definitely work. And so we oftentimes call that formula, or that form right here, r squared plus alpha minus 1r plus beta, this f of r. I don't know why it's called f of r. A lot of things in math are just tradition. But since we know that there are two r values, since it's a quadratic that should work, we can break them up into using the fundamental theorem of algebra into two linear terms. Note that r1 and r2 can be complex numbers, as we learned back when we were doing constant coefficients. But regardless, I can break them up into the factors r minus r1 and r minus r2 for two different roots. So, if we have two different roots, notice the Wronskian works out, best from the Wronskian, and they do work out because we don't want x equal to 0, and r1 and r2, when they're distinct, aren't equal to 0 when you subtract them. So, they are linearly independent if r1 does not equal to r2. Take a second for you to take a look at that. And so, consider this case. I have 3x squared y double prime plus xy prime minus y is equal to 0. That means y is equal to xr, y prime is equal to r, x to the r minus 1, and y double prime is r minus 1, x to the r minus 2. Plug that in, you get the characteristic equation 3r squared minus 2r minus 1 is equal to 0. That can be factored, or you can use the quadratic formula. That might be a little bit easier on this problem. 3r plus 1, r minus 1, which means that r is equal to negative 1/3, and r2 is equal to 1. creates this cool little Nike symbol here under these different when I have coefficient C1 being 1, C2 also equaling to 1. You can remember from the previous slide that if I did the Wronskian of these two, it indeed would be non-zero for all values of x greater than 0. If R1 and R2 are not distinct, if they are the same, we can do repeated roots or reduction of order just like we did for constant coefficients. In class, I kind of explained this a little bit. Remember, since our f of r is the product of my two terms, r minus r1, r minus r2, if they're r1 and r2 the same, it's like saying r minus 2 times r minus 2. Well, if they're multiplied together, it's just r minus 2 quantity squared. So that's what this is saying here. And so, what's that r minus 2 squared? That's just describing a parabola. What's the slope of the parabola at its vertex 2? It's just 0. So we talked about this briefly in class. If it helps you do the reduction of order, you'll notice that just like when we were doing repeated roots, we'd multiply by an extra t or x. So if I had e to the 2t, if I had 2 being repeated roots, I'd e to the 2t, then I'd have t e to the 2t. I'd multiply by t to get an extra linearly independent term. In this case, I need to multiply by the natural log of x. And it is indeed linearly independent when we plug it into our best friend, the Wronskian. So, consider the equation. X squared y double prime plus 7xy prime plus 9y is equal to 0. Surprise, surprise, it's going to be repeated roots problem. I get the characteristic equation, r squared plus 6r plus 9 is equal to 0, or r plus 3 quantity squared. Since I have repeated roots of negative 3, I get the characteristic equation, c1x to the negative 3, c2x to the negative 3 natural log of x, or as the slide puts out, c1 plus c2 natural log of x all times x to the negative 3, since there's a common term. Also, we can do complex roots. How do we represent complex roots? Because we don't like them. In the case of our polynomial, we don't like to think. We're perfectly okay with x squared or x to the negative 1/2, but as soon as I start putting something like x to the 2i, that's confusing. So, using the rules of logarithms and inverse functions, I can do x to the r. Well, e to the x and natural log of x are inverse terms, so e to the natural log of x to the r is the same thing as saying x to the r, because they're just inverse functions of each other. But logarithms allow us to move that pesky little, from your perspective, r, which was r. We have the x here, and we have r in our superscript in our exponent. I can move the r up front. And since r is our nasty little complex root, it separates into nice cosines and sines according to the Euler identity, Euler equation. I guess Euler identity. But this term right here, since our lambda is real, both lambda and mu are real, just I mu is imaginary. This term right here is all real number. This is all purely imaginary. So this needs my Euler identity, but e to the lambda natural log of x, reverse the process, and I get x to the lambda times cosine of mu natural log of x plus I sine of mu natural log of x. So you can write it as the same thing as we've done it before, or it might be easier to write it like this, where my y1 is cosine to the lambda, x to the lambda cosine of mu lambda natural log of x, and your y2 would be your x to the lambda sine of mu natural log of x. And these are indeed linearly independent if you were to plug them into the Wronskian. Notice that we didn't put it on this slide, but it does indeed work. Get the characteristic equation in this case. I'll let you think about it. It'll read through real quick, or pause if you need to. But the Wronskian is pretty straightforward. It's r squared plus 4, which means I have a lambda 0 and a mu of negative 2, plus 2. Well, a mu of being 2. So 0 plus or minus 2I is equal to r. So, since I know that my solution is the form c1 x to the lambda cosine mu natural log of x plus c2 x to the lambda sine of mu natural log of x. X to the 0 is 1. X to the 0 is 1. And so I get c1 cosine of 2 natural log of x plus c2 sine of 2 natural log of x. And indeed, for all of these, it doesn't matter when you plug in the theory. Your book, Boyce and Prima, does indeed prove this in a long and about way, but it doesn't matter if x is positive or negative as long as it's away from that singularity point at 0. So you can drop everything. You can repeat the same processes that we did before, both absolute values as our solutions as well, as long as x is not equal to 0. Hope this is helpful, and I'll see you next time.